Okay, in section 8.2 we're looking at integration by parts. Integration by parts is an integration technique that we use when we have products. A lot of times we might have a product of two functions. Trigonometric and transcendental functions seem to work really well with integration by parts, but actually a lot of other types of functions do as well. So first of all, keep in mind that this is a really good integration technique to use for products. The integration by parts formula is derived from the product rule. Now everybody learned the product rule a little bit differently. Some people used f and g functions. Some people used a u and a v function. So let's go ahead and look at this notation that we have. With the product rule, remember we were taking a derivative with respect to x of some function of u times some function of v. So I had two functions being multiplied together. So the product rule looks like taking the first function, which is u of x, times the derivative of the second function plus the second function times the derivative of the first function. So if you learn these with f's and g's, it's the same basic concept. Now from here, in order to derive the integration by parts formulas, you integrate both sides. So when you integrate both sides, you're integrating this sum, and of course the integral of the sum is the sum of the integrals. And then what we look at is we look at solving for this integral right here. So in solving for that integral, we end up with the integral of u of x v prime of x dx is equal to the derivative, or the integral of the derivative, of course, here will just be the functions multiplied together. Okay, and then we'd subtract this over. Okay, and so this is the integration by parts formula. Now when I think about the integration by parts formula, I think about it a little bit differently, a little shorthand, because this is a lot to remember. I think of it as the integral of u dv is equal to uv minus the integral of v du. So this is the integration by parts formula that I use. And we will definitely want to have this memorized. Okay, and again, the way I usually read this is the integral of u dv is equal to uv minus integral v du. U is a function, dv is the derivative of a function, u is a function, v is a function being multiplied together here, minus the integral of the function v times the derivative of u. That's kind of the easiest way to look at this. Well, I think the best way to go about explaining how to use the integration by parts formula is to go ahead and look at some problems. The first problem I'd like to look at is x times sine of x dx. Now when you look at this, you have to first realize that you do have a product here. I have a function of x and the function of sine of x. Now there's no technique that we have in our tool bag so far that would allow me to integrate this. If I let, just looking at the sine of x, if I let u equal x, du would be dx, and I'd be left over with this x. So using my standard integration techniques won't work. So we're going to use integration by parts. Integration by parts, IBP. Now when we use integration by parts, I want to match this formula. Integral of u dv, uv minus integral v du. So with integration by parts, I have to choose this left-hand side. So in other words, I need to make x sine of x fit this mold somehow. And then from here, this will give me my solution. So I need to take the x sine of x and I need to choose which one should represent my u and which one should represent my dv, and then I need to work from there. But one thing you need to be careful of here is that you can make the wrong choice. If you choose incorrectly, the problem gets more complicated instead of more simple, and then you're not going to be able to integrate it and you'll have to go back and choose again. A rule of thumb, this doesn't work every time, but a rule of thumb is that we let the trigonometric function equal our dv and we let our u equal the algebraic function. And again, it's just a rule of thumb, it will not work every time. So we let u equal our algebraic function. Now the reason we let u equal our algebraic function is we need to, if you look over here, I need a du. I need to take its derivative. Well, this is pretty cool. When you take the derivative of an algebraic function, a nice polynomial function, it eventually goes to 0, and it will get out of the way. Because that's the whole reason why this integral cannot integrate using our standard techniques, is the x is in the way. So I choose u to be x, and that leaves dv with sine of x dx. Now I wrote these in a particular way because pretty soon when we look at this, we're actually going to be integrating one side and taking a derivative of the other. So let's go ahead and look at that. So I need a du, the derivative of x is 1 dx, and then I need a v. So let's think about this one. As I move from dv to v, I don't take a derivative, I integrate. So looking down column-wise, I start with a function and I take its derivative. That's what's happening when I go down. When we move up, I start with some derivative, okay, and I integrate it to move up. So when we move down, we take a derivative, and when we move up, we integrate. The derivative of sine, in this case, is going to be a negative cosine of x times the derivative of x, which of course is 1. So the reason I have it written like this is that both of these across the top, u and v, are functions. Across the bottom are both derivatives. So let's go ahead and write what we have then. And another key to integration by parts is to always drag along the original problem, because pretty soon when we look at these types, we're going to be using a recursive method, and with the recursive method we have to have the left hand side, so it's important that we drag it along. So here's our original function, our original integrand that we're trying to integrate. The formula here is I should take u times v, so let's go ahead and do that. uv x, actually not x cosine, it's x times negative cosine of x, so that's my uv, minus my integral, and again that's coming from right up here, minus the integral v du. V is negative cosine of x, and du is dx. Okay, so again, dragging along that left hand side, the integral of x sine of x dx is equal to negative x cosine of x plus negative times a negative is a positive cosine of x dx. Finishing our rewrite here, I have the integral of x sine of x dx is equal to negative x cosine of x. Now, plus the integral of cosine. The integral of cosine is a positive sine of x plus c for my constant of integration. So that's my solution. And of course, I always drag along that left-hand side because we're going to need that in some types of these problems. My next question is can we check this? And yes, we can. We can take the derivative of our solution, and what should happen is I should get the integrand back if that works. So let's go ahead and look at a derivative here. For this first part of our derivative, I'm going to have the product rule. So I have the first times the derivative of the second. The derivative of cosine is a negative sine, plus the second times the derivative of the first. That's my product rule. Now I need the derivative of sine, which is a positive cosine, and the derivative of my constant of integration is 0. So let's try and rewrite this a little bit. It looks like we have negative times negative is a positive x sine of x minus cosine of x plus cosine of x. So these cancel, and I'm left with x sine of x. So yes, this does check because if we scroll back up, my original problem was x sine of x right here. So it does check. So remember, you can check all of these. And of course, that's going to have something to do with a time factor. You know, is there enough time to check all of these? But you should kind of get in the practice of checking those. It's good for your algebra skills as well. So that's an example of an algebraic times a trigonometric type of function. Let's go ahead and look at another one. This one's not going to really fit that mold, and it's just the integral of the natural log of x dx. And let's look at this from 1 to e. So let's have limits of integration here of 1 to e. Now, I don't see two functions here being multiplied together. It's not that obvious, but you actually do. You have the natural log of x as one of your functions, and the other function is 1 dx. So that's what we want to look at here for our choices. Now remember, the formula for integration by parts, we're going to use integration by parts, is the integral of u dv is equal to uv minus integral v du. So that's what we're looking at here. So what I need to do is I need to choose a u and a dv. I need to choose a u and a dv. Now, if I chose dx right here, I have to take the derivative of that. And the derivative of dx, I'm not sure what that would look like. It would probably look like d squared x for the second derivative, and that's not going to help us any. So let's go ahead and get rid of that. That was a bad choice. Let's go ahead and put the ln of x here, and that would leave just a nice little 1 dx down here. Now that's going to work. Plus, if I'd put ln of x down here in dv, I would have to integrate it, and that would be my original problem anyway. So, easy part here. Next I find du, the derivative of the natural log of x is 1 over x dx. So again, I take the derivative down and then I integrate up. So to find v, I integrate dx, which of course is just x. Following with my formula then, and dragging along the left-hand side, I get uv minus v du. So uv is going to be x ln of x minus the integral of v, which is x, du, which was 1 over x dx. And of course we have a little bit more room to do some work here. Integral from 1 to e of ln of x dx is equal to x ln of x. These cancel, the x's cancel, and this just boils down to minus the integral of dx. Well, minus the integral of dx is just going to be minus x. Now I do not have a plus c on this one because here I need to evaluate from 1 to e. So when I evaluate, remember you always do upper minus lower. So we'll plug in our e first. I have e ln of e minus e for my upper, minus my lower would be 1 ln of 1 minus 1. And of course a lot of these natural log functions we can simplify. The natural log of 1 is 0. So 0 times 1 is 0. The natural log of e is going to be 1. So that's e times 1. So this simplifies as well. I have e times 1 minus e minus 0. Now we have to remember to distribute this negative. And that leaves me with a plus 1. So this is equal to 1. So this is another way of saying the area underneath the curve of the natural log of x from 1 to e is 1, as long as the ln function is above the x-axis over that entire range of values from 1 to e. Now, if you wanted to double check this one, you could take a derivative as well. But where do you take the derivative? Don't take the derivative of 1, because the derivative of 1 is 0. We'd want to take the derivative up here to double check. So when we learned about the transcendental functions like e to the x and ln of x, we could not integrate ln of x before. So now we can actually integrate the natural log of x. And the strategy behind integrating the natural log of x is to use integration by parts.